All right, so this is our last part of the review for the Chapter 9 test, which is tomorrow. And we're going to cover the main two things are binomial expansion and induction. And those are the toughest two things. Now, binomial expansion would be like, for instance, if I had 2x minus 1 and I put it to the third power, there would be 4 blanks. It wouldn't be real tough to do. And you could use Pascal's triangle to find those lead coefficients. Just a quick reminder, you'd say 2x to the third, 2x to the second. What am I doing wrong already? Has to be parentheses, otherwise this 2 wouldn't get cubed. There we go. And then 2x to the first, and then 2x to the what? 0. Good. And then this next one will be a -1 to the 0, -1 to the second. Oh, sorry, first. -1 to the second, and -1 to the third. Effectively making this negative, this positive, because it's, you know, squaring a negative. This negative, and this positive. All right. Then the last part is you can get those numbers off Pascal's triangle, 1, 3, 3, 1, from this 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, because it's just that plus that makes that. But that breaks down as soon as you want to have, like, the power be 2x minus 1 to the 23rd power. You don't want to make a triangle that big, right? All right. I would like you to try to remember how you find, without Pascal's triangle, the second term in that big sequence. Everybody find all of it, not just that thing in front, but find the whole answer for the second term of 2x minus 1 to the 23rd. I'll pause for a moment. All right, so some thoughts. This spot right here would have been 23 to the, or over 0. That makes this spot 23 and 1, 3 and 1. And that means 23 choose 1, which means 23 factorial over 23 minus 1 is 22 factorial with an extra one of those, 1 factorial, which really means 23 times 22 times 21 dot 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 over 22 times 21 times dot 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 with an extra 1 factorial, which is just 1. So that all cancels, and that turns out to 23. That's this part right here is a 23. Raise your hand if you had that right. Okay, good. Next, this one. It's going to be that 2x to the, well, instead of 2x to the 23rd, that would have been first. This is 2x to the 22nd. So yeah, the 2 to the 22nd, that's a really big number, so I wouldn't have expected to be able to do that in your head. So you would be able to write that out as 2 to the 22nd and x to the 22nd. And then the last thing is really just going to make it negative or positive, and it's a -1, and you start here with -1 to the 0, so this must be -1 to the 1, and that means it is negative. So you should have had negative, and then this part was 23 times 2 to the 22nd, x to the 22nd. And I get that little multiplication there, just a little too hard. Raise your hand if you were able to get that one. Okay. Any questions? Things like that are going to be asked of binomials and the binomial expansion. Think you can handle it? Okay. Yes, sir. Okay. So which part? The 23 over 1, the 23 1 thing, does that part make sense to you?
Yeah, but then we put the 20. Oh, I see.
That was 23 choose 1, 23 factorial over 22 factorial, 21 factorial. You okay?
Yeah, sorry, I put a 22.
Yeah, as long as you know where your mistake is, you're good. Okay. So now, that's binomial. Last chance to ask me questions about binomial. Okay? All right. Okay, then let's gonna move on to the next thing, which is about proving that two things, proving a statement using math induction. All right. So we prove it's true for n equals what first? 1. Does it have to be 1? No, but typically you start with n equals 1. Then you prove that, this is the weak part, that you can swap out the n and the k. You're just changing, you're basically saying, I'm going to prove it for a number, now I'm going to prove it for a different variable. Well, that's the weak part because you're just swapping them, it's just rewriting. And the last part is k plus 1. You're swapping in n equals k plus 1. And that's the hard part that brings in a lot of algebra. All right, I want to look over one that you guys did on not last night's homework, but the night before, where it was day 2. So everybody look in your files for day 2, problem 2. Day 2, problem 2. We're going to talk over how that induction one went in a moment, well, after I pause. Okay, so here's the original problem. This is problem 2 off of that assignment. And it's very typical. So first you prove that it works for n equals 1. Well, that's easy. You stick a 1 here, you stick a 1 here, and a 1 here. Turns out that 6 equals 3 times 1 is 3 times 1 plus 1, which is 3 times 2. 6 equals 3 times 2, which 6 equals 6. You always end with an exact equality. There, proved it. Next, I got to prove it's true for n equals k. And so then it's just a rewrite of the original 6 plus 12 plus 18 plus dot 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 plus 6k equals 3 times k times k plus 1. I don't really need all those parentheses in there. There. Just swapping an n and a k, so there. Now, everybody look at your work and see if you found the right next step, which is the hard part. N equals k plus 1. Then this same exact statement applies. 6 plus 12 plus 18 plus dot 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 plus 6k plus another term, k plus 1. Notice I don't remove this term. Just like when you get an 18, you don't remove the 12. The 12 is there also. So I'm going to take 6k plus the next term, 6 times k plus 1. It's like I have this, except I'm putting a k plus 1 in it. All right, so there we go. Equals 3k, k plus 1. Now, think about that for a second. That's wrong. Because I just added something here and didn't add it to the other side. You're breaking the rules of equations, right? So this is the part where you should add the exact same thing over here. 6k plus 1. Are you with me so far? Now, this has to algebraically be solved down to what? The goal. The goal is to prove that the original statement, which is up here, okay, I'm going to clear out this stuff so that I can see it better. This red original statement would have been true if I'd have put k plus 1s here and here. So I'm going to write my goal down here in green. My goal is to get 3 times, again, n is going to become k plus 1. And then n again is going to become k plus 1. And then plus 1. There, that's this original statement with k plus 1s put in for the n. Now, I can drag this down the screen here, and eventually my right-hand side should equal this left-hand side. All right, so I'm going to take and start by, right off the bat, I'm going to jump into something hard. Do you get that k plus 1's in both of them, but there's more? I'm going to because if you can't factor, you should, right? And I see k plus 1, but there's more. Yes. A 3 and therefore factor out all at the same time. What? 3 times k plus 1 gets factored out because they both have a 3 and they both have a k plus 1 in them. So now, when you're factoring something out, you're dividing it by 3k plus 1, and that cancels and that cancels, and part of that cancels and that cancels. What do I have left? K plus, this was really 3 times 2, right? And the 3 part is canceling because we're dividing by it. And that's leaving me with 2. There we go. And I'm really close to this now, aren't I? By factoring out those two things all at once at the beginning, I got myself really close. Because now this plus 2 can be just changed. No, you can't just jump right to the answer. You have to show it. This, nobody could argue with you that 2 is the same as 1 plus 1. You know what I mean? That's a very reasonable step to take. And then the next step is the final answer, And all it is the exact same thing we had with parentheses put in there, because that is true, that I can put parentheses around that if I want to. And now that looks identical to the goal, and that means therefore true. Actually, I'm wrong. Therefore, I have proven true for n equals 1, n equals k, and n equals k plus 1. Therefore, true by induction. Throw in the word induction. That needs to be on the test. That's how you prove that you have actually done all the steps of induction. Yes? Sure. Go back to this original statement. The question was, can you show how I factored out the 3 times k plus 1? You have to look at the original. I'm going to get this off to the side here. And you have to see what is both terms. This is a plus sign, right? So that makes this a term and that a term. And what do they both have in common? It's pretty easy to see they both have a k plus 1 in common. Do you get I can factor that out then? All right. They also have a 3 in common, because I think of this 6 as 3 times 2. Now do you get they both have a 3 in them, just like they both have a k plus 1 in them? It's kind of like this. Would you agree that both of these terms have an a in them? So I can factor it out. Do you agree they both have a 2 in them? Because the 6 is really what? And therefore this, they both have a 2 and they both have an a, so I'm pulling out a 2a. And then what that really means is I'm dividing everything by 2a. And the 2's cancel, and one of these a's cancels, along with this 2 cancels, and this a cancels. And that leaves me with what? A plus 3, and that's what goes here. So it's kind of like that, except with more complicated things. So back to this guy. The 3 and the k plus 1, they both have a 3, and they both have a k plus 1. 3 and a k plus 1. And whatever's left is the k and the 2 go here and there. All right.
The only thing is that if you break that down into 2 steps, right, which is going to stack the 3 plus 1 by itself, you're going to be able to 3k plus 6, right?
Okay, hold on. If you factor out just the k plus 1, you would have 3k plus 6. Yes. Okay, wait. So I'm going to write that. If I factored out just the k plus 1, I would have 3k plus 6. Yep, you're right. It'll still work. This is just making it 1 step instead of 2. And maybe it would have been easier to just do it this way. And then take the 3 out now. And then move the 3 out to the front. So it actually saves you a couple steps. But anyway. All right. So that's basically the process of induction. Now, I wanted to have you practice that. I want you to do one yourself, because a lot of times in the homework, people try and fail. And I want you to get one from start to finish in class and get graded on it so you see if you're doing it right. So what I'm going to do is hand that out to you right now. And then after a period of time where I feel like most people are done, I don't want to stop and grade it, because then the people that are working slower are going to get burned. But I will stop and then do the review that I wanted to do for the final. In your hour, we're set to do the chapter 6 one. So anyway, that's enough right now for studying for math induction, other than we're taking this little quiz in class today. So that's all I have for the video for today, as I'll just wish you good luck on chapter 9.